Hey everyone, it's Kelly, and let's go over this problem. It requires a few steps, so it's kind of an involved question, but I think it's a good one to see if you can work out. We essentially have potassium chlorate that is decomposing into its potassium chloride and its oxygen. And it gives us some information which we'll go over, but in general, we want to calculate the partial pressure of oxygen right here and the mass of the potassium chlorate in this sample that's decomposed. So we are going to definitely use this balanced reaction because we need to know mole to mole ratios, but let's first figure out what it's actually telling us. So the O2 that's produced in this reaction is collected by just using the displacement of water, and it tells us that 1.20 liters was collected, and it told us that the total pressure that it had on the system was 760 torr at 22 degrees Celsius. So that's the information about the O2. And then we also have information about the vapor pressure of water right here, 22 degrees Celsius and 21 torr. Okay. So you have O2 that's produced in this reaction. And once you know the moles of that, then you can figure out the moles of the potassium chlorate, which would give us the mass of potassium chlorate. So kind of involved, but it should be an interesting problem. So let's start with what we are given. So we are given the temperature. That's the wrong brush. Let's go back to this brush. We're given the temperature of oxygen, 22 degrees Celsius. We are given the total pressure, 760 torr. What else are we given? We are given the volume of oxygen, which is 1.20 liters. And we are also given the vapor pressure of water, H2O, is 21 torr, and its temperature was 22 degrees Celsius. Okay, so with that information, we can actually start solving the problem. So let's figure out the first one. It says calculate partial pressure right there, partial pressure of oxygen. So essentially when this oxygen is being collected through the displacement of water, the only other gas that could potentially be available to us, kind of added to the system is the vapor pressure of water. So the first part is actually a one-step process. The total pressure is just going to be the pressure of oxygen and water, gaseous water. Okay, so we know that it's 760 torr, the total, because it tells us in the problem right there. That is going to equal some unknown P oxygen, but we know that pressure of water is given. It's 21 torr. So what does this give us? P oxygen must be 739 torr. Okay, so that is step one. We figured out its partial pressure, okay, what it's contributing to the system. Now, for part two, it requires a bit more work because we need to do some stoichiometry. So if we're given pressure though, right, if we have pressure of O2, don't we know an equation that can get us to moles, right? So for the second question, your ideal gas law comes into play because we can use PV equals nRT, where we know the pressure of oxygen, we know the volume, we know a gas constant, and we know the temperature. So the only unknown thing is moles. So let's rearrange it symbolically. N would equal PV over RT. Now let's plug in what we know. Pressure of oxygen is going to be 739 torr. So if you divide it by the conversion factor that gets you to atmospheres, then you can use the gas constant in atmospheres, which I like to do because that's one I tend to know the most. So this right here is the conversion factor. There's 760 torr in 1 atmosphere. So that would be essentially whatever decimal that would be in atmospheres. We have for volume 1.20 liters. On the bottom of this fraction, we have 0.08206 liters atmosphere per mole. I can't tell you how long it took me to remember those units. But if you ever forget what the units are for the gas constant, rearrange PV equals nRT, solve for R, and whatever what is on the other side of the equal sign are your units, right? And then our last bit right here would be your 22 degrees Celsius plus 273 Kelvin, right? Because we need to cancel this Kelvin right here. So it can't be in Celsius. Cool. Okay, let's see what we got here. So I ended up, if I am correct, let's hope I am, 0.0482 moles of O2. Now, if it just asked for that, we'd be done. We'd go home, make dinner, be cool. But we're not done yet. We need to do a few more steps because the second part of the question asks for mass of the potassium chlorate. Now, this is where you go up to the reaction, right? Because if you have moles of oxygen, you could figure out moles of either of the other components. But you need to make sure that the reaction's balanced, which I did that for you. So let's start. If we have moles of oxygen, I'm going to rewrite it right here, moles of O2. What do? We convert it to moles of potassium chlorate. So for every 3 moles of O2, we have 2 moles of potassium chlorate. If it wanted moles, we'd stop, but it wants mass. So molar mass, right? For every 1 mole of potassium chlorate, we would add up all the atoms, and I ended up getting 122.5, let's call it 55 grams of potassium chlorate. And in the end, I got 3.94 grams. So that is your answer for part 2. Essentially, if we had about 4 grams of this substance and we decomposed it, then it would produce that many moles and it would exert that much pressure. Okay, so this is a really good one. This requires using the balanced reaction, kind of deconstructing the actual words, the numbers in the words, interpreting the problem, which is always so difficult, right? So I would highly recommend to practice these types of problems because they really exercise a lot of dimensions to the types of pressure problems that you'll see in the future.